Assalamu alaikum. In our last lecture, we did until the types of structure of protein. So we learned about the primary protein or primary structure of protein, secondary structure of protein, and tertiary structure of protein, and how are they different from each other based on their bond types. So we have learned so far, and there was a homework which was to write beside whatever bond or whatever structures were involved in this bonding. So bonding tests are written here. So the first one is disulfide bond between the chain or between the parts of the chain. Then we have hydrogen bonding in beta plated sheet. Then we have ionic bond between parts of chain and peptide linkage between amino acids. So previous knowledge, like task class knowledge, was enough to answer this question. So I'll be giving the solution right now. So the first one here, disulfide bond, it simply it says the name itself defines it's from the tertiary structure, isn't it? So it is right with a different color. It is a tertiary structure. Okay. Now for the hydrogen bonding in beta plated, we also saw it's a direct example, direct picked words from there, and it's from the secondary structure, isn't it? So secondary structure, an ionic bond between parts of chain. So remember, this is also part of the tertiary part. There, it was in the third one was written the ionic bond between ionized R groups. So that's from tertiary. Last one, which is peptide links between amino acids. So peptide links between amino acids. That means what? Did peptide links are said? It didn't say, remember, it didn't mention hydrogen bonding between peptide linkage, okay? Rather, what? Rather, direct peptide bonds are there, only peptide bonds. So that means primary. Okay. You might get confused that in secondary structure, it is written that this is the regular structure arrangement of the polypeptide chain that result from hydrogen bonding between peptide bond regions of the chain. Now, peptide bond region, that might confuse you, but remember there is written hydrogen bonding. Secondary group only, or sorry, secondary structure only undergo or only participate in hydrogen bonding. Okay, let's move on. Just a second. Okay, sorry for that. So coming back to the spur. So today we'll be continuing with enzymes. And so I obviously know that you already know what are enzymes. So for the formulae, we'll be just getting back to the concepts, like what are enzymes. So enzymes are what? Biological catalyst. Biological catalyst. The biological catalyst. They are protein. Basically, they are protein actually. The enzyme, specifically, they are protein. And they have what? Active site. That active site is responsible for responsible for participating in reactions. Then we have substrate, which actually binds with the active site of the enzyme. What does that mean? That means substrates are the reactant, you can say. So substrate, ATE, substrate, which is also known as reactants. So what basically happens? Wait, let me write it down. Reactant binds with active site of enzyme. Should be the active site or active site? Okay, so basically, let's say this is the enzyme. Like normally the key chain pattern. Okay, we have this key chain pattern. Now, let's say this is the active sites. Okay, this is the active site. Most probably it should be sides. Side, yeah. Now, the reactant or the substrate is the portion which appears over here. So this is the substrate. Okay, this is our substrate. It appeared here in order to help it to help it to react, help the help the substrate to react or the reactant to react. Okay, so it fits on the key, on the lock part or the key chains part, key part, and like yeah, they fit in sort of a manner that they get locked. Hence, after reaction, substrate is broken away, forming two different portions. Okay, and we are left with our the catalyst remains itself, like it remains unchanged. Okay, now enzymes, they're specific to particular reaction. So specific, wait, enzymes are specific to particular reactions. Okay, why? Because the, let's say the catalyst for amino acid, like contact the Haber process, formation of ammonia. So in the Haber process, we use what? Iron as a catalyst. That might not be used in other reaction. For example, same catalyst cannot be used in the contact process. Contact process is which one? Formation of sulfuric acid. Okay, or sulfur dioxide to be more specific. From where? Or sulfur trioxide is being formed, and from there we get the what? Sulfuric acid when dissolved into water. So that sulfur, like production of sulfuric acid, there when V2O5 is used. I forgot the name, but this molecule is used. Oh, sorry, vanadium pentoxide. Yeah. So vanadium pentoxide is used in here in contact process. However, in Haber process, iron is used. So both have different, like in terms of catalyst, they are different for different substances in like real life scenario, like in our existing world. However, enzymes are what? Biological catalysts. That means they exist inside the human beings or inside the living creatures, like that sort of thing, isn't it? Or plants or whatever you say. So that means obviously enzymes will be specific to specific reaction. Okay, so they're different for different reactions, and they have, as I've said, the active, like they have an active site. Now, this active site of enzymes, they can be changed due to the change of temperature. Now, what does that mean? That means enzymes are very sensitive. So if slight changes, like slight temperature changes applied, let's say it works best at 33 degrees centigrade. So if you apply, let's say 35 or 36 or a little bit more, let's say 40, the property of the enzyme will have been changed. Okay, so that means it changes active site due to change in temperature. Okay, change in temperature. So that's how, or that's what it will. Also, if let's say pH value also changes, let's say some enzyme works best in like acidic situation, for example, amino acids. So other enzymes works best at, let's say, alkaline solution. So if amino acids pH is like this, let's say the atmosphere is made to, let's say this is the pH, like the amino acid in such a pH where the pH is low. So let's say I made the situation, I made the atmosphere in such a way that the pH rose to a high pH value. Now, how do we like usually increase the pH value? That means we actually apply some like some alkali or base is added, isn't it? That base can sort of react with this enzyme to change its active site. Okay, so active site will be changed of the enzyme. Okay, now the like as I've shown here already, the substrate reaction part, what happens, how it happens. So enzyme and substrate, they tend to come together, form the bond. After forming the bond, what happens? They like breaks, isn't it? This is what? This is a substrate. Substrate. And over here, what do we have? After like breaking it down, we have what? Products. And enzyme remains enzyme, isn't it? So that's what like is being like is the main concept here. So they might ask you to draw the like certain structure. So initially we have this end first, then the substrate is coming towards it. Let's say the substrate is coming towards it in order to react. After reacting, this is the state. After combining, this is the state, and after reaction, here might not be this part. Yeah. So the breaking part is after, like directly will be shown. Okay. So the broken part will be directly shown as product here. And yeah, that's all. Okay. So that's it's like some general information regarding like the proteins and amino acids. So there is this yeah, so there is this sickle cell, which is like MO. Wait. So sickle cell anemia, sickle cell anemia. So anemia. Anemia is it's actually anemia. So sickle cell anemia is a genetic based disease. Okay, so it is a disease genetic based, which like in which what happens is like one of the glutamic acid. So glutamic acid is the the structure of the glutamic acid is this one. So this is the glutamic acid. That means we have dicarboxylic acid as well as an amine over there. Okay, so sickle cell anemia. Sorry, sickle cell anemia is like actually like this is a disease. Okay, this is a disease where what happens is the glutamic acid residue is replaced by a valine residue. So this is a glutamic acid. So this gets replaced by a valine residue. So how does the valine residue looks like? Valine residue looks like this. Okay, so when this residue, like this amino acid, replaces this amino acid, okay, so glutamic acid is replaced by this one. So when that happens, this sort of genetic based disease happens. The name of the disease is what? Sickle cell anemia. Okay, it's anemia. Sorry, I keep on like pronouncing the wrong word. So I'm really sorry for that. Like it resembles the structure of like ammonia. So I keep on saying that. But yeah, it's actually anemia. ANEMIA. Okay. Now, what actually happens here? So the pH the pH of the area the protein would be like that will be changed. Okay. So pH of the area of the protein would be changed. pH of protein's area changed. Okay, that would be changed. Then the next information is protein becomes less hydrophilic, less soluble, more hydrophobic. Okay, so a lot of information. Let's break it down. So protein, protein, protein becomes less hyperhydrophilic. We know hydrophilic is what? That means it absorbs more water. So hydrophilic absorbs more water means it's also soluble. Okay, absorbing more water means it can react with water. So that means it's soluble. Or sorry, I'm really sorry. Yeah, hydrophilic means more soluble. Now less hydrophilic means what? Less soluble, isn't it? Like the opposite will happen. So hydrophilic means it absorbs water. Less hydrophilic means it absorbs less water. That means it is less soluble. Okay, so it is less soluble. Or we can also say that it is hydrophobic or more hydrophobic. Hydrophobic is the opposite to hydrophilic. Okay, they are just like antonyms of each other, or antonyms of each other. So more hydrophobic. Wait, hydrophobic. Okay, so fewer ionic bonds will be there. Since like they're less hydrophilic, that means what? They are less prone to react with water. And those components who like reacts less with water, that means what? They could be less ionized, because water is what? A polar solvent. Water is a polar solvent. There's partial positive negative charge. Anyone coming to them or dissolving in them does what? Forms bond with water molecules. Anyone which dissolves in water, they form bond with water molecules. Now, those who are less soluble, less hydrophilic, that means what? They're less soluble, like less dissolvable in water, so they react less with water. That means what? They're less ionic. Like fewer ionic bonds will be formed. Okay, because now they cannot form bond with simple water, a polar substance. How will they form ionic bonds with other substances? So fewer ionic bond. Fewer ionic bond. I'm sorry for the handwriting, but like just listen to what I'm saying and like keep track of them. Now, like the tertiary structure of the protein, okay? So, or the 3D shell of the protein, that will be changed, okay? When like these sort of things happen, what that means, this glutamic acid, when it is changed by this valine, okay, that's what it is being saying, that what happens after each of the situation is happening. Don't worry, I'll be explaining it again, just bear with me. So when this happens, tertiary structure or 3D shape of protein disrupts or simply changes, okay, whichever is easy for you. Lastly, the active site would be different or less efficient. Active site would be less efficient. Or we can say it would be less efficient. You can also replace it with different. It will be different. Okay. Now, let's have a recap on what we just studied. There, say, at first see, what do we have in glutamic acid? We have this carboxylic acid and amine, isn't it? We have 2 carboxylic acids. Now, having 2 carboxylic acid means what? We can donate 2 H plus ion. So that means 2 parts now, they can form bond with water, isn't it? That means they are more hydrophilic. Now see on the right side, one of the OH group or COOH group is gone. There's no COOH group. That means what? Less soluble, less dissolvable, less hydrophilic. Here, 2 molecules or two bonds, 2 OH bonds were present so that they can absorb water. Here only 1 OH bond is present. So that means less hydrophilic. Here 2 acidic groups were present. Here only 1. That means what? pH value changed, isn't it? pH of the protein changed. From glutamic to valine, pH value changed. Protein become what? Less hydrophilic. Now, since C double H group is not there, and we know carboxylic acid tends to undergo like or forms ionic bonds, isn't it? For example, carboxylic acid with sodium, what will they do? They will react with each other, forming what? Na plus and O minus. This will be the case, isn't it? This will be the structure, C double O minus Na plus. It means ionic bond. So since we don't have, we're not having a carboxylic acid group over here, that means what? Fewer ionic bonds will be formed, isn't it? Fewer ionic bonds will form, and tertiary structure will be of the, or the 3D shape of the protein will be disrupted. Why? Because see here, like here, the structure, there is only single double bond. Over here, there's like double bond. That means over here is one, another is over here. Now, this molecule obviously its shape is going to be a bit different, isn't it? Because compared to this part, this portion has like over here is one bond, there's another one, there's another one, there's another hydrogen bond which is imaginary, isn't it? Because that's a carbon here. But here, what do we see? There's directly like three distinguished bond. One is here, and another is here. Though this part is what double bonded, but that's with a single atom, isn't it? That means what? Three-dimensional structure, the tertiary structure of the component will be disrupted. Finally, the active site will be less efficient. Why? Because the active site reacts with certain portion which, like in enzyme, we're talking about enzyme, isn't it? Because proteins are what? Proteins are like also enzymes. This enzyme, these are actually proteins. So that means when glutamic acid is changed to valine, obviously this carboxylic acid is not present there. That means proteins, this amine, like this carboxylic acid was responsible for forming that protein, isn't it? So that's what happened, because this is the portion, let's say this is the amino acid, and this is the R group, isn't it? The R group changed here, isn't it? See, the R group actually changed. Again, let me show what I tried to make sense here is, this is the amino acid, isn't it? This is the amino acid, and this is the portion where this is the R group present. Remember, see the structure of the amino acid. This is the R group. So R group actually changed. Changing of R group causes this sort of changes, like this sort of drastic changes in the characteristic, and that's very feasible. Active site would change. Why? Because one R group which sort of, let's say, form a hydrogen bond or form ionic bond. Okay. In this case, this is what? This is a tertiary structure protein, isn't it? Because it has a carboxylic acid group, and we know tertiary structure have what? They can form ionic bond, isn't it? They can form hydrogen bond. So this carboxylic acid, they can form ionic bond, hydrogen bond. So this is a like tertiary structured protein. Since these disappear to see what? A complete alkyl group. That means what? Now this is a primary alcohol. Sorry, primary acid. So there is this a primary acid. Wait a minute, let me see. Like there's two CH3 group, or this is CH, CH3, CH3, but still, like this is, as I mentioned, there could be many amino acids. Like R group could be many different type of R group. Okay, so valine is not given. Like we didn't learn valine in, like, to be more specific. Yeah, we didn't learn valine to be more specific, but like makes sense. Like try to make sense. We studied about whom? We studied about alanine. So alanine was what? Just simply CH3 was present there, isn't it? But here we have like some other alkyl group, but still that's an alkyl group, isn't it? This is an alkyl group. That means what? Only van der Waals forces of attraction will be present here. Other than that, no other bond is present here. That means what? Obvious tertiary structure changed to a primary structure, isn't it? So that's what it's saying, that the active side will be changed, tertiary structures, the shape will be changed. Okay, so that's what they're trying to mention here. Now let's move on to our next part, which is formation of the disulfide bridge. So we'll be learning what, like how this disulfide bridge is formed. So formation of disulfide bridge. Okay, so that's what we are going to learn. So we obviously know so far how it works, but for simplicity, let's learn directly. This is our like nitrogen. This is our, let's say, some other like amino acids group. So we are having, let's say, some polymers here. This nitrogen forms bond or has a bond with this what? Its inner carbon, hydrogen, and there's the R group. So the R group is CH2SH, okay? And that carbon is bonded with, let's say, a carboxylic acid. In this case, a peptide linkage has been already generated, okay? So that like it goes on. Let's say this is our hydrogen, and there's that bond. Like it continues. Okay, it continues. So this is our actual portion. This is our actual like amino acid part, but like the repeating unit part, and these are like they will continue. This is just, let's say, a polymer chain, and we have just taken a stanza from there. So one of the portions has been taken, and let's say are repeating like exact same mirror image, identical part is over here. That's the hands free. This is CH, and we have here CH2 and the SH, let's say. So we have a like sulfide group here, and NHC double bond O, and like it continues. Okay, over here, these two portions are like responsible for forming this such bond. So what will happen here actually? What is going to happen is over here, this portion, okay, that is going to cause the reaction to happen. So the hydrogen will be like disappearing. So two hydrogen will be like disappearing. That means what? Loss of hydrogen. Loss of hydrogen was what? Oxidation. So oxidation is actually happening. Okay. Since like not necessarily we have to gain oxygen to have oxidation, or we have to, let's say, like lose electron in order to like have oxidation. Loss of hydrogen could also be oxidation. So that is what happening. And when that happened, simply this bond will be formed. Okay, and the rest will remain same. So there will be C, and like it continues. Okay, so there's a hydrogen, like it continues, and there's our C double bond O group. There's that NH group. There we have NH C double bond O. Like it continues. Okay, here like you got the thing. What happened? What is happening? So this is the new portion which has been formed here, the disulfide bridge. So this is our bridge. Okay, now let's see that in place of, let's say, long chain carbon or a long chain polymer, how this happens. Just like over the surface view, let's say we have this let's say we have this long chained like polymer. Okay, like thing in microscopic level, we somehow gathered this single chain, like this chain of like polymer or like a polypeptide. Okay, a polypeptide was somehow like managed to like get from here. Okay, now let's say that over here the carbon from this portion, like the CH2 is CH2. So from this chain, like same chain is there, but a portion from here to a portion from here, like they tend like, or they sort of formed what? A disulfide bond here. So this was our, or this is our disulfide bond, disulfide linkage, disulfide bridge. So disulfide bridge. Okay. Now, not necessarily only this will be formed here. Since this is a tertiary structure, we have what? 4 different types of bonding, isn't it? So let's say, let's draw the other portions as well. Let's say we have here's some CH3 group, and here's some CH3 group. They will have van der Waals forces of attraction between them, isn't it? They will have van der Waals forces of attraction. So this is van der Waals. And similar chain, let's say, let's say this is our C Yeah, let's say this is CH2 COOH, and here we have CH2OH. So this alcohol and this carboxylic acid, they will sort of have some like sort of interaction bond or interactive bond. What sort of bond will be here? There will be hydrogen bonding. Okay, because oxygen, like hydrogen from one oxygen and hydrogen from another oxygen, or oxygen from like oxygen bonded with carbon. So C has this carbon, or like oxygen has this carbon on the carboxylic acid, and on the alcohol we have what? We have OH. So this, sorry, in the opposite way, we have this H and O, like O bonded with H. So this H will form hydrogen bond with this that oxygen. So that's sort of what happens here. So that's some hydrogen bonding. The last bond we have is, let's say, the amines part. So we did have a like amine there. So let's say that amine somehow form NH3 plus after gaining electron. Sorry, after losing electron, I mean after gaining a hydrogen, H plus ion, and one of the carboxylic acid from other molecule, that's CH2COOH, so that becomes CH2COO minus. That means this acid lost an hydrogen, this gained a hydrogen. Between them, some strong ionic bond is formed. That means this is a what? Ionic attraction. So see, in the same chain, if that's a tertiary structure, like tertiary structured protein, they can have all the 4 bonds present in the same chain. The opposite can also happen. Only one type could be present, or let's say like some of the portion or some of the bond could be present. So either can happen. Okay. Now, like what type of bonds are actually causing or being produced here? Let's have a short like information. So one of the bond is what? Let's say this is the continuation of bond sign. Okay. So let's say this is our CH2 4. So here we have already like the hands-free means like we have the existing bonds that are existing. Like the rest of the molecules are bonded with this portion, like this hyphen sign portion. And we have what? NH3 plus bonded with, let's say here is O minus and OCH. Sorry, there was CCH2. And here's the bond, it goes on. Okay, that's one of the bond. That's what? That's our ionic bond. Then we have CH2OH that forms bond with whom? That forms bond with our carboxylic acids portion, let's say. Like this portion, double bond also COH and CH2. And hence it goes on, okay? So that's that interaction between them. So this is what that is, hydrogen bonding. The first one is ionic bonding, the second one is hydrogen bonding. Then the third one, let's say we have the disulfide pair, like breach CH2 S CH2. This is the third bond, and the fourth bond was the CH2 4. Wait. The third one was CH3 with, let's say, CH3, and it goes on. Okay. So that means what? There was that Van der Rohe process of attraction. Okay. Now that was the part for our protein. Now some interesting concepts we'll be learning. So DNA will be our topic from now on. So what does DNA means? It is deoxyribonucleic acid. Deoxyribonucleic acid. Okay, so DNA means that. Now there are some like bases for DNA. So specifically, we have nitrogen bases there. Nitrogen bases present there. So some of the nitrogen bases are adenine, which is represented as capital A. Then we have guanine, that is represented as capital G. Then we have thymine, and finally we have what? Cytosine. That is represented as what? C. Now, deoxyribonucleic acid, how its structure look like? How does its structure looks like? Let's have a look at this sneak peek at towards its like structure. So we have, let's say we have the skeletal structure. Finally, we have what? This is, let's say, that portion, CH2. We have that oxygen there present, and we have, let's say, hydrogen here. Finally, we have, let's say, this H here, OH here. Like I'm just drawing both skeletal and like the like a mixed structure. I'm just drawing a mixed structure. So, and here we have the OH group. Okay, so that's sort of like how the deoxyribonucleic acid looks like. Okay, or to be more specific, we can also draw a bit like in there. That's the structural formula. So CH, I mean the split formula, CHO. We have CHOH. We have here then CH and H here. Then we have, let's say, COH there. This carbon is bonded with that oxygen. There's this H again here. I have CH2 and OH here. Okay. Now, for simplicity, like to make it this look much more prettier, let's say we have this oxygen towards the middle. So that means this oxygen is bonded with two of the carbon to the other sides. Okay. So the next parts will be continuing on the next part of the video.